Right, and much work, much credit goes to Darby Dyer, co-author on this work, and it's been supported by Vortice as well as the laser. So thank you to those funding sources for this. And the work presented in here done at APL. But as a background, spectroscopy is used to determine the composition of surfaces. These are standard techniques, been around for several decades, and you can see up here some spectra from the Relab as well as from the test library at ASU. And Reflectance spectroscopy is good using crystal field transitions to look at absorption features in pelagic clays as well as pyroxenes and olivines. And this is a terrible viewing geometry. Anyway, and similar things here as well. Amazingly, this does show up very poorly here, unlike on the preview screen. These are thermal emission spectra or reflectance spectra, emission spectra actually from the test lab. Not that important other than they work, okay? But they don't always work. Thermal emission spectroscopy and reflectance spectroscopy, the usual wavelengths, don't always tell you the information that you need or want to get to understand the surface composition. This could be for several reasons. One of them could be simply there's no illumination, which is what we've been talking about quite a bit here at this survey and NLSI presentations. At the lunar poles, where permanently shadow regions, clearly can't use reflectance spectroscopy at the traditional wavelength, so the sun doesn't shine there. And thermal emission spectroscopy doesn't work because the surfaces are too cold. And this could be true also for shadows anywhere else, or for objects far in the outer solar system where the sunlight's very dim. Other reasons why it may not work is because the surface composition itself does not lend itself to these measurements. Surfaces that have been bombarded or irradiated quite a bit, space weathered quite a bit, have more shallow bands than they do traditional rocks. Although with that said, there is quite a bit of successful use of shortwave infrared spectroscopy and infrared spectroscopy for determining the composition of the moon. However, when you look at glasses in the laboratory, it is a prime example of how, although the composition of these glasses show that there's an iron feature here consistent with olivine, these are actually glasses. There's no olivine in these materials. And the iron abundance varies greatly, as you can see, from 0 to 20%, with no strong correlation between the band position, band depth, and the amount of iron in there. And thus, if it were a mineral, the mineralogy, though it's a glass, so it's a composition. Brightness does change, as well as the slope or the visible albedo. But again, there are many space weathering processes that can fool you there, so don't use color to judge the composition of the surface. Similarly, thermal infrared can be hampered in some ways, although well, because it's the glass, there are Strahling regions which basically focuses on or leverages the lattice vibration is absent because, well, there's no long order range, and so there is really no long order lattice to work there, and the Strahling bands all merge together, and your volume scattering goes away. Everything is very highly emissive, or in this case, very low reflective. Christensen feature is where the absorption is strong. However, the N, the real-index diffraction, approaches 1, so your scattering drops to 0, and so you have emissivity peak or a minimum in your reflectance. And Diviner has been very successful in mapping it generally to the surface of the moon. But you can see in this case, the correlation is there, but it's not all that strong. So we're looking for cases, well, can perhaps UV help in some of these relationships? And it's not the first time people have thought about using UV spectroscopy to look at surface composition. LAMP, after all, was flown on LRO to look at the composition of ice and characterize the surface of the moon. And Gladstone et al. In 2011-12 has done some very good work, as well as others on the LAMP team. In this case, they are showing that perhaps there is water ice in one of these craters, which I really can't see right here. This one compared to that one because it's bright at this wavelength, and whereas this one's dark. And you can do a ratio showing, I don't want to get into too much detail, but I will later, that you can potentially find water ice using UV spectroscopy. And one point I want to bring up at the end is with appropriate spectral resolution, you can actually tell the difference between ice and pelagic clays. And also, Amanda Hendricks has done some interesting work on Vesta, although in that case it's a HED meteorite is well resolved, or its composition well resolved by near-infrared spectroscopy. But with that said, the UV is quite useful in mapping out iron, or I should say transition element composition, due to the presence of a strong band around 200 to 300 nanometers due to the oxygen metal charge transfer, actually any ligand to metal charge transfer in the mineral. And this is from a 1974 transmission spectrum from Siegel, who looked at different glasses doped with calcium, sodium, potassium, and saw very interesting trends. Didn't really explore it too much, but they do exist. And later on, following on that work, reflectance spectroscopy was conducted by first Hatke and Wells in 1981, using a setup in their lab. And following on their work was Wagner et al. In 1987, who really has done seminal work looking at the composition of many different materials from lunar surfaces, etc. And you can see, yes, of course, magnesium olivine actually looks somewhat like plagioclase here, no absorption band, perhaps. Okay, so maybe it'd be hard to tell, although in the thermoinfrared you could tell the difference. Iron-rich olivine, very strong 1 micron band. But in UV, what is interesting is that the position, and this is better resolved in data I'm about to show you, the position and depth of this OMCT absorption band can be used as a tool to look at iron abundance. And I want to get into that now, and this is the laboratory setup we used. This is a central vacuum chamber down to UHV pressure, so that's not too important for this. On the left is the UV monochromator, and the light is illuminated 25-watt deuterium light source. Goes in, reflects off a sample, and is detected by PMT. What's important in this setup is that you have a very good reflectance standard. I'll get to this in a second. Well, anyway, reflectance standard sample holder, we use about 90 milligrams. We can control temperature as well as pressure, of course, and other things with it. We choose to use magnesium fluoride because it is a very reflective material. It's basically the window material you use in the vacuum UV. So by using powdered magnesium fluoride and volume scattering, the light is reflected back out of it. We don't rely on first surface reflections or just very white opaque materials like a paint. Instead, we use this process. You could think of it kind of like snow at visible wavelengths. It's white. Snow is a little blue, but largely white. This is in comparison to barium sulfate, which is a traditional standard. This is measured in my laboratory. Reflectance of the powder, and you can see it begins to drop off strongly around 300, and it's very, very dark at 150, even 100. And the measurements I'm going to show you goes down to this wavelengths. Now, this isn't absolutely terrible. If you can actually characterize reflectance, this can be used as a standard, if you know that's what it is. The problem, though, is that if your standard is dark here and you have any scattered light, then you're going to have a brightening of reflectance spectrum here because you're dividing by a small number. But then you're actually adding a small bit of scattered light to that number, and so it's going to affect your results quite a bit. Okay. So instead, I use magnesium fluoride here as transmission spectrum. It's really good down about 200 nanometers. There's a knee in it, about 160. You actually see that in my correction factor that I get to right about here. So this is iron, very iron-rich glasses. I make the a priori assumption that these glasses will stay dark, i.e., flat at these lower wavelengths due to a combination of various oxygen metal or ligand metal charge transfers and absorptions. Looking through the literature, different, not just Siegel, but other literature as well, it does look like the iron-rich silicates should stay dark at those wavelengths. Modeling would need to actually confirm that. And of course, then I looked at water ice as well after I did my correction to confirm that water ice actually does look correct after I make the corrections. But anyway, this doesn't look believable. I correct for it. You can kind of see the knee here at 150 nanometers. So I'll correct for it. Boom, there it is. Of course, I corrected for it. I also removed a first surface reflection off a window, about 4% reflectance there. So this is what we get before we correct the spectrum of water ice using the before we correct for the magnesium fluoride. Water ice looks like this. Okay. I.e., if we just assume mag fluoride was flat all the way across. But correcting it the way I just showed, then the water ice ends up looking the blue line, and it flattens out down here, which is consistent with what Hendricks and Hansen reported in 2007 for fine-grained water frost. So at least that is consistent. Okay, great. Apply that further on. So apply this correction to not just the very high iron materials, but also to lower iron material and anorthite, iron-free glass, water frost. You can see this OMCT band here, and the band actually is saturated here because there's no continuum, but we do the saturation goes away, or there is a continuum starting about 5% iron abundance. And then, interestingly, there still remains a OMs or ligand metal charge transfer band in both anorthite or the iron-free glass. Position is dependent on probably the structure of the materials, as well as perhaps the composition. And there's a knee here, very interesting. Okay, in that you can compare it to water frost. In a way, the anorthite or glass is similar to water frost, except they have this OMCT band. So by using UV spectroscopy, as I get to, you could differentiate water from iron silicates, and you can differentiate iron silicates from each other at low abundances. Also, this technique is not dependent on mineralogy. It's looking at composition only, so you don't actually lose the absorption feature because you have glasses. The analyses I did are very simple. I simply looked at the band position and band depth using simple band continuum removal band depth analysis. So we find a trend with total iron abundance. So these glasses were made years ago. The oxygen free gas was not that well controlled, so the Fe3+, Fe2+ varies. Fortunately, it doesn't vary monotonically with iron abundance, so we actually look for whether there's a dependency in the OMCT band characteristics with, with the Fe2+ or 3+. And amazingly, when I plot either Fe2+ or Fe3+ versus that band depth, there's no correlation. Only by adding these two together is there a strong correlation, implying that this OMCT band is really not that sensitive at all to the valence of the iron, which is somewhat unexpected, and we're working on that. Or another way to say I don't understand it. Okay. So draw a trend line, and it's kind of interesting as well. The intersect should be band depth about 2 minutes. Okay. So if we add titanium to it, kind of like the trend a little bit better. Titanium is the reason why I add to it, because there's titanium in these glasses. I'm basically not adding titanium. I'm saying, okay, the near UV band depth versus the total amount of iron titanium, what does the trend line look like? And it looks a little bit more reasonable in that perhaps we can draw a line like this, but we don't have enough data points. We need to measure more glasses to really understand the correlation between this band depth or perhaps band position and the abundance of these charge transfer elements in there. But it is quite promising that there is a relationship here that can hold with composition. So in addition to understanding silica composition, how can we use this to help understand the composition of water ice? So LAMP data, basically they're saying here that it's dark in the far UV, in the shorter wave UV, everything's dark there. Water ice, though, stays bright until close to far UV, so it's bright here in the near UV or not so far UV, whereas other stuff is dark. So this is probably water ice. But what about this stuff? That water ice with all these other bright features I pointed to. Well, it's possible that UV spectroscopy can help on this one. Don't want to get into this too much because I am out of time. Instead, I'll simply say this. Water froth, glass, anorthite. If you mix the ice and the glass together, correct? Yes, it can look rather like anorthite. In other words, if you don't have the spectral resolution or the spectral sampling, you might confuse anorthite with a mixture of a little bit of water ice and maybe some glassy iron-rich material on the surface. But with appropriate spectral resolution to picking out, for instance, the position of this OMCT band, UV spectroscopy would be able to distinguish and differentiate between these different compositions between water frost, iron-rich glass, anorthite. Removing that disambiguity, or perhaps even explaining why these spots might be bright and look like water ice, even though they may not be. Just a hypothesis, because we have not looked at the data to do that. So it's just a thought I put out there. So in conclusion, I'll leave these up here because I believe I haven't really made up the time, have I? But in general, UV spectroscopy is useful because it keys on features that are not used at other wavelengths. These features key on elemental composition. They are not strongly dependent on mineralogy, perhaps not even dependent at all on crystal structure. So more resistant to space weathering. We haven't explored effects due to radiation damage, including the presence of nanophase iron, which occurs in lunar-style space weathering. But those are for future measurements. This is just beginning, so we want to make more laboratory measurements. And we think it's quite relevant to asteroids and meteorites. Oh, and the moon.
Thank you, Carl. Any comments or questions? Yes.
Thank you.
Identify yourself.
Tim Glotch, Stony Brook University. Just because I'm kind of ignorant about the UV literature. Do optical constants exist at these wavelength ranges for kind of the compositions we care about to do,
at these
quantitative
wavelengths,
mixing?
which is basically from 140 nanometers to all the way up to 450 nanometers, no, it's hard to get good optical constants in the below 250 because of the lack of standards, or in transmission, you have to use vacuum UV measurements, so not a lot. Okay. So no, not a lot of optical constants.
Carl, your UV spectra look really nice. I have a question about the character of your glasses, and maybe you talked about that and I just didn't catch it. Because you did mention that the oxygen fugacity wasn't controlled on these.
Correct.
Clearly, the near-infrared spectra of glasses are very dependent on the oxygen fugacity. And you're probably aware of the Bell and Mao work with a very well-controlled series of iron titanium glasses where they showed the absorption properties and the charge transfer properties at the 400 nanometer wavelength.
Yes.
So how do your glasses compare to their glasses?
Like I said, the oxygen fugacity wasn't controlled, so we do know the Fe2 and Fe3 plus abundances in them. I have not compared our IR reflection spectra to the Bell's results. Ironically, now that I look at our talk, all that work I did is not in here. But we do have reflection spectra of these glasses at those relevant wavelengths and could make those comparisons. But or maybe it was in there. Anyway, no, I did. It is in here. So this strangeness in here may be due to the changing Fe2 plus, Fe3 plus. So that's point, yes.
Yeah, and they showed that very nicely.
Okay.
So yeah, it'd be worth.
So point taken, yes.
Okay.
Okay, Darby's keen to get going here.